presentation, and I hope it will be interesting for you. I am Jean-François Carounos. I am a computer scientist at the CICG, which is a computing center for the universities of Grenoble. I will talk about an application which I'm currently developing, and this application is based on metrology data, and the goal is to improve the security of networking computers. And this application is called NetSec, for network security. Please understand this concept, because this application is more a concept than an application. This presentation is divided into two parts. And to start, we talk about metrology, why, what, and how can we use it, and some point of view about analysis. And the second part, describe the NetSec application, what are the goals, what is the architecture, what are the available tools, and then it will be time to conclude. But let's start with the first point, metrology. And why do we need measurement? This is the main reason, we think, and the first is to know the network usage. For example, who does what, when, and how. The second, to know the network availability. For example, is there any traffic congestion? Are servers and services well distributed on the network? Another reason is to detect dysfunction. Is there an abnormal rate of collision, or broadcasts, or from errors? And also to do cost sharing, to issue accounting in production to network usage, for example. And in addition, metrology can also be used to improve the security. But how and what can we do to measure? We distinguish two measurement types, and the first aspect is the qualitative aspect, and the goal is to know its network, to know how data flow takes place in the network. For example, what is It's okay? Sorry. I start this slide. We distinguish two measurement types. The first is the qualitative aspect, and the goal is to know its network. For example, what is the I/O traffic load, what is the CPU load, and what is the collision. And to do this, you can watch the counters in the routing equipment, for example, and with SNMP queries. The second aspect is a quantitative aspect, and the goal is to control its network. For example, you can, for example, the traffic type, what the protocols, the ICMP, the UDP, or TCP, the I/O traffic load for one host or several hosts, or one group, several groups. And to do this, you need to extract information from frame analysis, and sometimes with external devices like a sniffer. In addition, another feature of metrology, maybe less developed, is to use the huge amount of metrology data to watch on the network in order to take care of its integrity. Of course, the goal is not to spy, but to ensure network availability and quality of services. To do this, we think
we think that metrology-based supervision should be built on this principle. Supervision must be done daily, even shortly, sometimes 15 minutes is enough. And supervision must be done using curves or bar graphs. The idea is using a graphical format that human can easily understand and remember. Of course, GRNET values are explicit, but it's very difficult to memorize and to analyze it. In the other hand, the appearance of a curve or a graph is easy to remember. And we can summarize it by, to control and to manage a network, you must visualize its behavior. For instance, if you look at these two graphs, you can see the traffic, the normal traffic in the leaks in the CICJ on the first April last year. And on the second graph, you can see the same curve, except these two peaks, and the first just after midnight, and the second between 2 and 4 o'clock. And maybe these peaks could be an attack or an anomaly. However, at this stage, we are helpless and we can only take note of these anomalies. And we have to go back to analyze the traffic in the involved period. To do this, this is the first point, you need to have an history to analyze the abnormal highlighting traffic. The second point, when you dispose of this history, is to browse into it. To browse into it to analyze the traffic data. In the other word, you must locate the involved source and destination host when the date and the time, the intrusion method when it's relevant, and the extent of the damage. To do this, we think that we can use metrology data to do cross-checking and to sort this data on several parameters. To do this, you need powerful sorting tools. And in this orientation, and it will be the second part of this presentation, we are currently developing an application we have called NetSec. This application has 3 main goals. The first is to have an evolving software, scalable and adaptable to every site. The tool must be usable from a small campus network to a metropolitan network. The second goal is to analyze well-known data. That is to say, to analyze data provening from metrology platform commonly used in French university, French environment, especially NetMet and IP traffic. And the last goal is to support open standard in order to ensure easy distribution to everyone, especially to network administrators. To achieve this goal, and the goal, of course, is to improve the security of the networking computers. To achieve this goal, NetSec is built around a relational database because this system is well adapted to sort, to extract a huge amount of data, and moreover, SQL language is powerful and standard to extract selective data with several constraints. The second principle is to have a network, a simple network description in order to fit to any organization. Another point is to have a modular architecture to allow everyone to adapt it to the use of its framework software if needed. And the last goal is to use open source softwares. And this choice is made to ensure agreement about the solution and to have an easy distribution even for a small entity. The next slide lists the software we use. For the system, we use a Linux system with a Red Hat distribution, but you can use another distribution like Debian. It's not a problem. For storing data, we use MySQL database because it's very easy to install, provided by the Red Hat distribution, and commonly used in French university. To display results and to communicate with the NetSec system, we use an Apache web server with a JServe extension which provide servlet technology. And you guessed, all our programs are developed with the Java language. But let's turn your attention to the database. To respect standard constraint, database accesses should be realized with a JDBC driver. And about the queries must be very simple. Without embedded queries to allow a basic database system use and an easily write and understand queries. And the last point is to use one loader to put the data, to populate the database for one collector. I remember to you that the collector are NetMet or IP traffic. We'll come back just later on this point. If we look at the structure of a database, the relational schema is very simple, and we use a daily table to store data. And this table has this structure, this attribute, the source and the destination address, the date, the port, that is to say the number of the services between the source and the destination, the protocol of this service, and the volume exchange between the source and the destination address. And another table is used to describe the network. This table is an association of 4 items, and the first is the number of the network in the CIDR notation. The second and the third describe the organism, an entity. If the organism has a big size, you can cut it in several parts. And the last item is the location of the network. For example, this network belongs to the CICG, which is a part of the University Joseph Fourier, and the CICG is located on the campus of Grenoble. In this structure, we dispose of some tools, and at this stage, 3 tools. The first is the data query module, the second, a graphic generator module, and the last, a data mining module. To well understand this architecture, I sum up the NetSec project in this figure. As you know now, the data is recorded in the database. And to populate it, we use a collector. A collector is a metrology software like NetMet or IP traffic. The data are exported in a text file, and then we put it in the database with a specific loader. For example, a specific loader for NetMet and a specific loader for IP traffic. Then we can put in the database the network description with another loader. And now NetSec can provide services through this data. The first tool is a tool to query data from a list of HTML forms. We generate SQL queries, and to return the result in the browser of an user. The second tool is a graphic generator tool, and the goal is to provide graph of a determined service or traffic to supervise it. And the last tool is a data mining tool, still under development. We are just the first result at this time, and the goal is to research information in the database, no information, of course, and to send it, and to send new knowledge to administrator, for example, by mail. About the first module, the goal is to use the SQL power to sort, to extract, and to query data. For example, you can provide outside networks having the biggest network traffic volume with an internal organism or an entity or a specified host in a slot time. Another example could be to have the top uses of network ports between internet, for example, and an internal organism or an entity or specified host. To do this, NetSec provides a web interface. On the left of this page, you can see a list of predefined queries, and to start it, just click on one and you display it. Sorry, it's printed in French. In the next release, I will translate it in English. And for example, this page provides the top traffic in byte coming from the internet to an organism or to an entity, which is a part of an organism, or a location, or a network, or all these items at the same time. If you prefer, you can specify with this text file the destination address. Then you can specify if you want to have the DNS resolution. After, you need to specify the start and the end of the date, the number of results in the result page, and if you like, you can sort results by services, for example, with web service. If all is correct, you will submit the request, and the query engine takes the parameters to process it, load the JDBC driver, and open a connection with the database. Then he built and execute the query according to the parameters, and you return the result to the browser, Netscape or Internet Explorer, of the users. As you can show on this slide. Here you can see the SQL request which is generated by the query engine. In the real use, this query is not displayed, just for this presentation. After you have the result, and then the information you are provide, which you provide in the previous form. Now let's move on the second part, the graphic generation tool. The goal is to have a zoom on a network on demand in order to supervise a determined services. For example, if you look at this page, you can see the in and out HTTP traffic from and to an entity. The first graph represents the daily activity, and the second graph represents the weekly activity. On the second graph, you can see that the HTTP activity is different since Saturday. This is the week activity and the weekend activity. And it's because it's the weekend. And why? Why this activity continues on the same way on Monday? Because this Monday is a public day in France. And as I said in the first part, in the metrology part, to highlight a problem, you must have a graphic representation of the behavior. This is a very simple example, but you can easily discern or see differences with this graph. To ensure it, the graphic generation module takes data, use data in the database, and the data query program developed for this need query the database and return the result to an external software, MRTG, for displaying. And then MRTG display the result, build the graphic. The MRTG graph are something like this. And to draw your attention on security problem, I'm showing you another example with SSH. This page shows the in and the out SSH activity in terms of accesses from and to the CI/CD. On the first graph, you have the daily activity, and it seems to be correct in terms of number of accesses, because the number of accesses is not too important. And on the second graph, you have the weekly view, and if you look at the scale, you see that the number of accesses is very important, and you can think that every peak represents an attack on SSH service. Now, I'm going to present the last part of the NetSec project, the data mining tool. The goal is to produce unknown, non-trivial, and of course useful information stored in the database. The idea is that the database holds information about communication flows. And we are expecting to anticipate problems and to raise alarms to administrator in order to take an appropriated actions. And to do this, we propose to use a technique of data mining, the technique of association rules. The rules look like this. For example, an item A and an item B implicate an item C. To generate such a rule, I propose to you to watch the association rule process. This is an iterative process in 4 steps, and it starts from the database. The first step is to select useful data, useful attribute of the database, because all attributes and transactions are not especially useful. Then you have a set of transactions. From this, the second step, the goal of the second step is to extract items having a support more important than a user-given threshold. The support is the number of occurrence of an item in the set of the transaction. And then we can produce association rule. And for example, if you are in a supermarket, such a rule could be cornflakes and sugar implicate milk. And then supervisor can take an appropriated action to place items in the shop. And then the next step is to see this rule and to try to extract new knowledge. For example, let's generate such a rule. This is the frequent item set. This is, for example, the day of the week, the number of services, that is to say the DNS, the number of the volume of data between the source and the destination address, the vulnerability of the service according to the CERT organization, according to the weekly information provided by the CERT organization. And the last item is the time slot. This rule comes from 1,000 rules which have been produced using data of 1 week. And it's very difficult at this stage to produce new knowledge. We need to try to work on this point. And to conclude this presentation, we saw a free contribution to improve the security of networking computers. This contribution is based on metrology data built on a database. This application is open and modular, and of course, the tech is under development, and some parts are particularly focused, such as data mining. And however, the following points should be improved, like software distribution and packaging, the documentation, and the automatic archive to archive data in CD, for example. And if you are interested, you can contact us at this address. Thank you for your attention. If you have any questions.
Okay, we think we have time for one quick question.
How much experience do you already have with this? Did you actually find stuff other than the example that you showed?
We have 1 year of experiences, just 1 year. But the last tool, the data mining project, just only 1 or 2 months, and just the beginning.
And I didn't quite get what you mentioned, these NetNet and this other product. What's the parameters that you then actually store in the database? Is that just load, or are there other parameters as well? You store number of packets, number of bits per second, I guess, or
I don't really understand the question.
So what are the things you measure that you put in there? All of them.
To collect data, we use metrology software, and the data are always the same: a source, destination, port, protocol, and so on. And after we put it in the database.
And how many different places do you collect that? In one place, or?
I can show you on the figures.
I'm sorry, then
And this figure, this is the GRNET metropolitan network, and we connect on this routing equipment. We are a router on this point and on this point, and the amount of data for a day is approximately between 2,000 megabytes and 1 gigabyte of data.
And the database, would it be difficult to extend the database to collect data from multiple points?
We have not things about this point now.
Okay, thank you once again. Okay, the second speaker of this afternoon's session is probably somebody that needs very little introduction. He should be well known to most of us. He was one of the early pioneers of the European Internet, one of the founders of the RIPE organization, and was also instrumental in establishing the RIPE NCC, the first regional IP registry. These days he can still be found at the RIPE NCC in the role of chief scientist, I think your title is.
Yes, that's
and working on various projects of interest. His title of the presentation this afternoon is Measure Well Before You Manage, a personal view of recent advances in network measurements.
Yeah, and that's the first one I have to punt on, but I'll tell you in a second. Actually, I like the previous presentation very much because it actually makes mostly the same point. When I got asked to speak here, my plans were to attend a conference or a workshop that's called PAM, Passive and Active Measurements, this year, and basically report on interesting stuff I saw there. But due to some personal circumstances, I couldn't attend the workshop. And due to other personal circumstances, I had minimal time preparing this. So it will be slightly different than advertised, but I hope it will still be interesting. That's basically what I said. But I want to, for those of you who don't know the PAM workshops, I want to briefly introduce them. They're basically intended for people doing research in measurements things. The first one was in 2000, actually. I forgot to put them on that slide, in New Zealand. And the next one will be in early 2003 in San Diego. But if you're interested in what's happening in this area, then what you want is basically look at the proceedings. And lately I'm getting tired in writing down URLs. So my personal way of writing down URLs is Google and some string, and that will take you there. And I'm quite sure PAM 2000 will take you there as well. I very briefly, the only thing I had to go by was reports of people who were there, plus the proceedings, and this is all on the internet. I just want to do a few highlights, and maybe people who were there can help me if I forget anything special. When I read the proceedings, talked to people, I found that there's actually work starting now on retrieval and distribution of results. And the previous presentation was actually already in that vein, and I didn't know about it. It wasn't there. But the idea here is basically we measure a whole lot, but getting to do something with it really needs some ways of standardized ways of getting at the results. And there's some initial work going on there. So people who are interested in that should certainly look this up. There's finally good results on path loading, or the other way around, this is bandwidth available. This has been going on for a couple of years already, and everybody wanted this. And finally, it looks like there are tools there that can actually, on a given path from A to B, can tell you what the available bandwidth is. And that's, I found that significant because it's been going on for a long time. And there's some results basically measuring application behavior and most notably DNS behavior. So that's also interesting. You can find the proceedings on the net, basically Googling to PAM 2002. So since I didn't go to the conference, I thought, well, this is about network management, and I said I was going to talk about measurements. I decided to talk about something I know about, which was also presented there, and that's our little thing that we do at the RIPE NCC. And I have to say, and that's the reason why Henk's name is on the slides and was on the first one, that I blatantly stole his presentation he made at the last RIPE meeting. So those of you who know TTM already will probably be bored to death, and I apologize. What are we doing there? That's basically active measurements. So it's the A in PAM. And the main goal of that project is to do performance measurements, and I'll explain a bit why we should be doing this. What you see is the user's view, usually, and they say, the internet is slow today. And what that tells us is, A, they don't care and they don't know about what's inside the cloud. And what they're really interested in is end-to-end performance. So if you want this web page to load quickly, you want your voice over IP traffic to get there with minimum jitter. Basically, no, you're not interested about the jitter. You're interested about you being able to talk to the other guy and things like that. Then, of course, the current approach, or the mostly known approach, is that you basically, what most ISPs do, or network operators do, is they SNMP their boxes and basically use the boxes inside the network to measure themselves, and they get very good knowledge about what happens in particular spots. And But can you add that up? And it turns out that you usually can't, because you don't get the whole picture, because the equipment is owned by different people. If you really look at it, it's different things. And sometimes not even the things colored the same. For the things colored the same, there's people who know really all about it. We found that out. It's really interesting. And then you've got all sorts of other things. So what you really want to do is you want to actually do an active measurement and just pretend you're a user to a certain extent and see what kind of performance do you get. So if you look at it from the other side, not from the user side, but from the service provider side, is okay, we want to provide, as a service provider, good service to the customers. And then the usual questions are not sort of, is the internet slow or not, or what kind of end-to-end performance do I get, but things like, are my boxes working properly? Actually, are the boxes from the people I peer with or the people I get upstream service from working properly? Which they sometimes don't have an immediate interest to tell you. Do we meet our service level agreements? Do they meet their service level agreements? And basically do some engineering in the sense of extending your networking. Where do we need more capacity and things like that? And anybody who's in that business will tell you that answering them is not easy. So we have the user who's interested in end-to-end performance. The performance that the user sees is, you cannot just add up a number of parameters that are, and you don't have all of them to start with, so that won't work. And even sort of, if you look at it from where the user wants to go, usually it's not a single provider who basically provides that. So our solution is to go and measure end-to-end performance parameters. What can you measure? You can measure routing information. That's basically state of routing tables, churn of routing tables, so how frequently does it change, things like that. And you can do that at an individual router, or you can do that at an autonomous system. And that depends on whether you're interested in internal or external routing. You can look at delay or latency. That's basically so how long it takes for a packet to go from A to B. You can look at packet loss, how many don't get there. You can look at bandwidth, and that's what I referred to earlier, that we're now getting, looks like we're getting tools that can actually do that. And you can look at quantities that are derived from the above. So there you have delay, IPDV stands for IP delay variations. No, is it IP delay variations? Yeah, IP delay variations. And sort of the EE people call this jitter. So that's the difference between delays on successive packets, which is an interesting parameter for things like voice over IP, where maybe the absolute delay is not so important. If you like, people are listening on the network to this presentation, they don't care whether it gets there a second later. But if there's too much variation, the sound will be intermittent, and that's annoying. Well, I think people know that. Reordering is a big issue for much the same reasons. And then there's sort of, you can even go down to the applications and see sort of what kind of, look at what kind of network behavior they want and try to measure the parameters that are necessary there. Everybody uses ping, I guess. That's basically a round trip measurement. So if getting from A to B, it sends a packet from A to B and then back from B to A. Does this very nicely low on layer 3. Interesting thing there is that while the standards say you have to implement it and you have to answer those things, nowadays you will find that that's no longer true. And actually, strictly speaking, all the equipment and configurations that don't do that are not conforming to the standards. But okay. So that's one problem with it. It doesn't work everywhere. The other is that it gets specially treated in very many network elements. And there's another paper about this in the PEM 2002, which actually the gist of it is that it's not that bad, not as bad as one thinks. But still, they're getting that's treated differently. The other problem with ping is that it's on if the delay on the A to B is not the same as on B to A, you can't measure that. You can only measure the sum of them, and you can make no inference whatsoever about what it is in one or the other direction. So with a ping measurement, you cannot say anything about, well, with a ping measurement, you cannot say anything about the individual components. If you measure one-way delays, you can just add them up to get the two-way delay. So it's better to measure the one-way delay. Unfortunately, it's not as easy as measuring the round-trip delay. And that's because on the round-trip delay, you can use the clock in the position you're doing the ping from. Whereas if you do one-way delays, you have to have synchronized clocks. You have to synchronize the time between the two places. Otherwise, it won't work. And that's basically because the reason why that's harder to do. And yeah. So the one-way delays, there are several things out there that can measure one-way delays. We built one of them. What do we measure? We measure those one-way end-to-end measurements. We put dedicated measurement devices out there, so we're not using the boxes that are actually transporting the traffic or to measure themselves, but we put dedicated boxes there that basically behave or can behave just as end systems, and depending on what kind of traffic we send, that traffic can also just be treated like any other end system traffic. It's active measurements, so yeah, as I just said, we can basically emulate real traffic. The other nice thing about this is that it doesn't raise any privacy concerns. We're not sniffing any traffic off the network, so we don't have to guard it with our lives for privacy reasons. It follows well-defined IETF standards. So yeah, focuses on external networks. So what we wanted to do, because of the role of the REP NCC in the scheme of things, is to concentrate on measuring between different ISPs and between ASs. But you can use the same techniques to look at your internal network as well. And since about 2000, we offer, about 2 years, we offer this just as a black box service. So I just want to show you what you can do with it. Let's assume that you have installed one. You get a lot of a number of products from it. One is some active things, like the previous speaker was suggesting. You can warn the user by basically alerting them. And there's also passive ones where you actually have to spend the 15 minutes, and I like that very much. I like the 15 minutes, and I like the graphical things. You have to spend the 15 minutes a day, and, well, Hank says less than 5 minutes a day. Depends on things, but I don't think it's an order of magnitude difference. And you can look at that in our particular case. You can look at two different things. You can look at online, or I would say real-time things in near real time, so 1 or 2 minute delay, and you can get a much more full-blown analysis, not in real time, the next day. And for this, it depends on what you're looking at. The main reason for this is that since we're measuring only one way, if you're interested in the two-way things, you only can get that by looking at the data on two different measurement devices. So on the online version, you can get delays into yourself by looking at your own measurement device, but you cannot get delays between yourself and the other sites, because you'd have to look into their measurement devices, and then you get into all sorts of problems. So we have two different ways of looking things. You can get real time, but not that much, and really already pre-digested information, or you have to wait a day and you get a really nicely pre-digested, nicely presented stuff, and I'll show you how that looks like. We also do trends. So when you participate in this for a long time, you can look at stuff over several months, which is quite nice for actually capacity planning and things like that. We added recently delay variations, and we will be adding bandwidth or have we added bandwidth already? But okay, it's one of the plans. The alarms I refer to at the moment, we do them by email. And what you get is something like this, and it basically says that on the 19th of April at 5:55 GMT, there was an alarm was set, and that we do by basically looking at collecting long-term averages for particular periods of the day, for different periods of the day to catch working habits of people. And when the averages of the long-term averages, or you should say the other way around, when the short-term averages significantly deviate from the long-term averages, then an alarm is generated. So that is done to prevent as many false alarms as possible. And in this particular case, what you see here is that the alarm was set. You can also get a message when the alarm gets cleared again. And that basically says the long-term average for this time of day is, and we had 2,200 some samples, is like an average of 2.5, a minimum of 2.0, and a maximum of 3.0 delay. And this morning, the short-term, the last 59 samples showed 10, 10.5, and 11. So basically, you have a jump of 8 that was put in there. So something happened here, and if you subscribe to the alarm service, you get that email, and you can have a look, even if you weren't planning to do your network meteorology that day. And then you get, and the same message, you get the URL here, where you can actually go and look at a graphical representation of this, which I believe is on the next page. What I have to do, yeah. So then that will take you to your own test box. And you will basically see that exactly what happened here is this jump in 8 milliseconds, but you don't have losses here. So you could then go and say, okay, what destination is this to, and relate it to some event in your network. So that's useful. The other is the full analysis, which is done on a central machine at the RIPE NCC. So all those test boxes send their data back to the RIPE NCC, and you get a web page like this, where you basically have a traffic matrix and for a particular box, so that might be yours, and you have along the y-axis here, you have the different destinations that you're measuring to, and you get summary numbers here, and we color them if they got worse or better to the previous period. So, and you can get this for day, week, and month. If you then zoom in and you see this red thing and you click on it, you get basically delay over time plots, things like that. So you have the last day, for instance, which shows that here for this particular one between 7:30 or something, what is it, 8 a.m. GMT and something like whatever 1400. There was a jump there, which might indicate a routing problem, and you can look at this for the last week and also for the last month. This is, and the previous speaker said it should always look the same, and we pretty much adhere to that principle as well. This is our standard, so what we had since the beginning, plot for a particular relation or connection between boxes. And you can get this for day, week, month, or some user-specified range, where at the top left you get a packet delay again. That's the similar graph that we saw before. So this is a week here from January 14th to January 21st. And you see, it almost looks like what you see on an oscilloscope if you have a square wave. And I already also saw some that really looked like electrical data. But anyway, so you have that here on the left, and then on the right you have the distribution. So basically the delay is on the x-axis, and the number of measurements is on the y-axis. So you get the distribution. You see basically that it's got 2 peaks here, plus a very long tail with some stuff. And then you have on the bottom right, you have the number of packets that actually arrived. So the white area is the lossage. And you won't be surprised if you see that at the periods of low delays, the lossage is minimal, and at the periods of high delays, you actually lose many packets. Another example is this is an example for the interface that we have where you can sort of individually say, I want to look at this from this to that time period with this resolution. The previous plots I showed here, these prepare, so you can basically click on them and they come up instantly for the last day, the last week, the last month. These ones you can basically request as you go. That depending on the time frame that you want them, if you want a whole year, that's going to take a bit longer. I think we have the wrong audio here for some reason. Anyway, I'll just continue on. And so here you see actually what happened on this plot here is the red line is actually something superimposed on the delay plot, which shows you the number of hops, so the number of routers that were in the trace route, which we also collect. I'll show you that in a minute. And we multiply that by 10 and plot it in here so that you can have a graphical idea that the routing changed there. And you see it's a bimodal distribution here, so you have this and this, which corresponds to this level and that level, and somewhere around 245 here, the routing change. Now, if you're interested in what happened with this routing change, you can click here on that link, and you get. Oh, there's the explanation I just gave. Fine, and you can click there. And you find basically this trace route plot, which basically says these are two of them put next to each other so that you can see it, which shows you that this particular one went this way before the event, and that way after the event, and Henk colored those the ones that differed in red. So you see there's one more hop. And there's also a slightly different routing here than there. And to protect the innocent, we anonymized it somehow. And the other thing is, if you look at things that are longer than a couple of months, we provide trend plots. So you can, if you request a longer period, the format changes. And there we basically divide the data into brackets of different timers of day. The same thing we use for the alarms. We have night, morning, afternoon, and evening. And so 6-hour periods, and plot the delays over the time period. And this one is a really interesting one, where you see sort of until about here, everything was nice and dandy. And then something changed, and what you see is that actually during the night it continued to be okay, yeah. But during all the other periods, it actually got worse, and then at the end it was even congested at night. And if you can see, you can put a line through this and actually see it deteriorates, and that is something that sort of is enormously appealing to network operations people to put under the nose of their management. To make their case for certain investments or extended capacity. Next thing, how am I doing for time?
About 3-4 minutes.
That will be fit perfectly. We have the next thing is basically the delay variations. That's a new thing we put in there, where you see that most of the connections actually are very well behaved there. But some of them actually, you see behavior like this. But this is the well-behaved one, which basically, what's plotted here is the difference of delays between successive packets. And if you have something like the top thing here, then That's something where you basically just get random queuing delay variations. But here you have, obviously, there's load sharing going on on part of the path. So part of the traffic goes one path and part of it goes the other. And from the shape that you can see that sort of the chance, roughly speaking, the chance of there being a negative offset of 4 milliseconds or positive offset of 4 milliseconds or no difference is distributed such that you can see it's basically random which path was taken. So either it is random or the process that decides which path to take runs much, much faster than our measurements. Bandwidth is the next one we're going to add, and there's some tools to measure total capacity, and there's also some tools now, and I mentioned that earlier, to measure what's available. The methods are based on packet dispersion. We're currently beta testing and deploying this. Have we deployed this already? Yeah, we have deployed. So for the people who already have this, they can taking part. They can actually look at this stuff. And the methods are actually one of the methods is described again in the PAM workshop. So how do we do this? We have you basically have to install a measurement device, and as I said, since you have to synchronize clocks, it's a bit more involved than just loading some software on a computer or putting in a computer. So you have to put a GPS antenna somewhere, and the problem with those antennas is that they have to actually have a view of the sky. You can't just put them inside a building, and since many of the places where we actually want to measure are in basements somewhere or hardened locations, as they would say, that's a problem. But we've designed, from the experience we had with this, we've designed a way of doing that by basically only having the antenna to be the antenna is the only, and that's this odd-shaped thing here. It's about this size, and you can see in the exhibition area, you can see a real-life version. That's the only thing that's remote from the box, and between the two, you can use UTP wiring. So if you have a chance to get to the place where you want to install this, you get to a window that has a reasonable view of the sky, it would work. And you only if you have UTP cabling in the building, you can basically patch it through. And we provide this as a 1U or 4U rack mount PC. GPS antenna, you need to be a roof or window, and the distance between the two can be 250 meters of UTP cable. And we provide this plug and play. Basically, you can go and get it, and we'll run it. This is the quite recent sort of geographical distribution of the boxes that are there at the moment. Topologically, they're also well distributed, but we'd like a couple of more to make it more interesting. This is the blatant advertising. You have to buy the hardware once because we want to do a turnkey product, and then you get a service contract, and the service contract basically includes that we produce all the results, and all you have to do is look at them. These are the contract addresses, and there's at the exhibit outside there's some examples of it. There's some folders and things like that. Yeah, I think measurements, and that's not only the conclusion from this, but also from sort of looking at what people are working on in the research area. Measurements are necessary to get a good idea of what end-to-end performance actually is. To do a good job at the measuring, you can't just have the network elements do that, or graft on something, just load a little tool and do it. To do sort of real industrial strength stuff that you can defend in the sense of it being giving a fair representation of what end-to-end performance really is, you have to use a measurement device, and we have one. And that ends the talk.
Okay, thank you very much.
And I apologize again. I apologize again for not giving the real overview that I planned to give, but there were some circumstances that prevented me from actually being at the PAM workshop and preparing this.
Okay, we have maybe time for a couple of quick questions.
Mike.
Comment really, just one other use that we found of the TTM, and that is in JR.
Oops.
Thanks. We find that the active alerts of transitions in delays are very good as an indicator that a GRNET knock ticket is on the way in the next few minutes.
Yes.
Thank you.
Okay, any other questions? Okay, in that case, I'd like to thank Daniel once again.
My pleasure.
Okay, the final presentation of this session is going to be given by Igor Velimirovich, and hopefully I pronounced that nearly correctly. He's currently the Chief of Network Monitoring and Measuring Department of GRNET, which is the Croatian Academic and Research Network. And he will be talking about active measurements on wireless LANs.
Yes.
No. Yes. Okay, good afternoon everyone here in the room and also all the people who are watching this via internet live streaming. My name is Igor Velimirovich. I work for Croatian Academic and Research Network. And of course I have a very difficult task today to keep you awake after the lunch break, which is not always so easy. The title of this presentation is Active Measurements on Wireless LAN. The simple question was put in front of this project team, and this question was, what is a real useful bandwidth on wireless links? Since these wonderful techniques that the previous speaker mentioned about using the tool that can give you the answer, what is available bandwidth on your route or end-to-end or on a specific link, we used a different approach 1 year ago, and we used active measurements. So first of all, the goals were to test a real transport characteristic of wireless links. That means that we wanted to know how effectively those links can transport IP traffic in terms of traffic load. Secondly, we have already implemented this wireless network in our network, although we always tend to connect all our nodes with wires traditionally, but we introduced some of our nodes, which are for different reasons weren't able to be connected with wires. We connect them using wireless links, and in this implementation we decided to go on 2 different manufacturers. So in our network there are 2 kinds of devices implemented, 2 different manufacturers, operating of course on the same standard. And of course the task of this project was also to compare those 2 devices and maybe give the answer which one suits us better. So those were the limitations, of course, of the project, because this project was just a given already implemented network, already operational. So we should only deal with the design of the network as it was. We couldn't change it. And secondly, encryption was enabled on all devices all the time during the testing. And of course, you will all know that encryption is a process which is time and processor consuming, and of course some of the results are affected strongly with this fact. Short overview of devices. We had, as I mentioned before, 2 devices which we, through this paper, refer as device A and device B. The first one was Cisco's, the second one was Lucent's. Not so important. They operate all on the same standard, which is 802.11b standard, released somewhere in 1999, which proposes wireless connection using speed 5 or 11 megabit per second. We used 11 megabit per second, and which operates on frequency band of 2.4 gigahertz, if you may know. These devices, so on the standard point of view, are same. Although device A introduces encryption which uses 128-bit encryption, while the other device, device B, uses 64-bit encryption, which is a little bit different. I mentioned that later in the presentation when it is important. Our network was already implemented and operational, and device A we had only one operating mode implemented, which is point-to-point. Device B, on the other side, was implemented in a point-to-multipoint operational mode with omnidirectional antennas, but of course we knew at the start that we should compare two devices when operating in a similar conditions, so that should be kept in mind. How our network looks like, this is of course on a logical scheme. Network device A was introduced in a network only in point-to-point operational mode, of course with two devices, with two antennas. On each side we had standard local area networks, Ethernet with Ethernet switches, and of course we introduced traffic generators, these dedicated boxes. I will cover them later on. Device B, of course there's a mistake on the slide. Device B was implemented in such operational mode that we had one device equipped with omnidirectional antenna in a location called location 4 for some reason, and the other three devices were equipped with a bidirectional antenna pointed to that antenna. So all locations had similar configuration of the network. A local network and traffic generators were put on each location. So as you may see, we had 5 locations, 5 traffic generators involved in this testing. How this network looks like, this is a partial map of the city of Zagreb when all the locations are marked. These acronyms means acronyms of our institutions. Most of these are faculties. And you can see the distances. Device A was implemented point-to-point operational mode between this and this location, FAIR and FKIT. The distance was around 600 meters, as you can see, and the other the location FKIT was equipped with device B also, with omnidirectional antenna, and 3 other locations connected to it. You can see the distances. On this slide, I must comment also the current situation in the city of Zagreb about pollution of the media, which in this case is air, of course. In Zagreb, there are no, at this moment of time, there are not many providers who offer these wireless connections. So we were lucky at that time. No interference was seen. Very few service providers offer this service, and they don't take much of the market. So for now, situation in Zagreb is very good. We don't have any problems with interference with other devices or something. So we are not highly polluted like some other European cities are at the moment, as far as I know. Yes?
What's the elevation situation there? Is it all pretty flat?
Yes, it's pretty flat, and these are all the tallest buildings in the area. We had a very good line of sight, no interference, no buildings between. So we chose, I think, the best location possible at that moment. So there, in fact, this faculty building is the tallest in the area, and it covers very well this part of the city, and there is no, the line of sight was achieved between all the locations. So we introduced a technique called active measurement using traffic generators. Since we decided to use 5 boxes, we do have some dedicated boxes, traffic generators, to use, but we wanted to make it as simple as possible and for the purpose of this testing as cheap as possible. So we used a very simple and relatively cheap solution. We used very old PC boxes, Linux-based, so very old processors, Pentium 46. As you can imagine, we used software traffic generator, program called MGen, which is of course free. This program enables you to create traffic of UDP type. You can configure this traffic in some amount. For example, you can change the packet sizes and so on. And the maximum speed of generated traffic relies heavily on PC power, processor power. And in our case, our test showed that this traffic generator, software traffic generator MGen, is able to produce up to 8.5 megabit per second. On this platform, on this very old and relatively slow platform. One may think we are using 11 megabit nominal speed wireless links and we want to test it with 8.5 megabits. But as you may understand and know, this is not a limitation at all because nominal speed of 11 megabits is not a realistic one to achieve. We will cover that later. The measurement technique was pretty much standard this way. SNMP-based tool collecting data from the boxes in some simple period of 1 minute, and of course data stored in database. In our case, we use this MSQL database, lightweight database machine. Not MySQL, not mistake, it's MSQL. So I talked about nominal speed of 11 megabits. The standard proposes this speed. But as you may see, useful bandwidth relies strongly on several parameters. And those parameters are, we divided those parameters in 3 groups. One is, of course, design issue. That means how many devices you want to put in your wireless network. And we weren't able to touch that because we have given design of the network, but as you may see, only 4 devices in one network. This was not the issue here. Quality of devices, manufacturer and price, I don't think I should comment on that. You know all about it. And of course, weather conditions, distance and line of sight, these parameters which can be changed during the time. So as I mentioned before, we were very lucky. Weather conditions in Zagreb are most of the time good. The distances were up to 600 meters, which was, I don't think, medium range for such links. And the line of sight was established between all the links. So if you have set it up all ideally, theory says that you can achieve 11 megabits, but what we saw there, that this number is, of course, much, much lower. Okay, results. So we've done 3 separated group of tests. First, we took device A, put it in a room, and tested in so-called laboratory conditions. Second, we went to the site and tested those devices on operation. Of course, device A was only tested in point-to-point operating mode, as was implemented in the network, and device B we tested in point-to-point and also to point-to-point multiple operating mode. And here are the results. First of all, test in lab with using these packet size of 1400s. The ratio between transmitted and received speed, not a very good term to use, but I will explain what does it mean. So we used MGen software to slowly increase the traffic load on both sides. So we used traffic generators on both sides of wireless links, put it in a room in laboratory conditions, and slowly increased it during the time, and then measured what was actually received on the other side. In point-to-point configuration with this device A, it enables you to configure manually which device get to be master and which device get to be slave. And this is very interesting that a master device gets a priority at the moment where congestion arrives, so-called congestion. So what we established that when we increased traffic load on both sides at the same time, at the point of time where those amount of traffic reached 3 megs on both sides, that was first bottleneck. At that point of time, this master device got a priority and was able to transmit more. Got priority over the media and was able to transmit more, while slave device, of course, he lost his competition with master devices in order to get to the media. And maximum amount of traffic which was seen on the link at a certain point of time was around, I don't know, 4.5 plus 2. That means 6.5 until 7 megabit per second in the laboratory conditions on a distance of a few meters. On the site, test showed similar results. That also confirms that our weather conditions, line of sight, and everything was set up pretty well. We used different packet size, and this was done in such a manner to see, of course, we all know that packet size distribution in our network varies depending on the application you are using and so on. And we wanted to see for some of the packet sizes, and these are 100, 200, 500, 1000, 1400 bytes packet sizes, how effectively can those wireless links transport IP traffic. As you may see, for very small packets, for the device A, the very low maximum speed was achieved, about 2 megs. And that doesn't matter in which direction we transmitted packet. This one means that we transmitted packets only from master to slide. That means that we only activated traffic generator on master side. This is vice versa, of course, and this is measurement when we started both traffic generators on both sides and then measure the total amount of traffic on the media. Of course, the reason for such a difference relies on encryption. Encryption has to be done for small packets in a harder way, so we think that the reason why this difference, such a big difference is there, relies in encryption. So maximum speed were up to 7 megs. Device B was more complicated to test. As you remember, it was implemented in point-to multi-point mode. So first testing was only done on this link between location 4 and 1 using these 2 traffic generators. So first this one transmits and then we measure, then this one transmits, then we measure, and then both transmit at the same time and then we measure. And also this was done on using 2 links at the same time and using 3 links at the same time. So that's why we have 3 results here. And each of the graphs shows for different packet sizes the results that were achieved. As you may see, device B is pretty much constant. No matter what was the packet size, the achieved results was pretty much the same. And of course, we see that total amount of traffic is higher if you put direction in both ways. So that was a good news for this device. Of course, I have to remind you that this device has only 64 bits encryption. So the issue of smaller packets is not so strong here. And now, how to compare those 2 devices. So we put all the results together, and we used the results of device B when operating in point-to-point mode. And we see significant difference. So device B has some advantage for smaller packets. And we think it was about encryption and encryption key. What was it? But for bigger packets, device A has clear advantage. Those were the results, and now I'll just make some comments about future work. This was, of course, only testing which provided us with the answer what was the amount of traffic or useful bandwidth that you can achieve using those wireless links. Of course, we know that applications do not rely exclusively on bandwidth, mostly yes, but not exclusively. There are some other parameters, for example, time parameters, like previous speaker mentioned, some variances in time delay, which can be measured, and some work has to be done in this area, focusing on those time parameters to see those time-sensitive applications, how do they react on such links or such links. Secondly, we just performed node-to-node measurements. And of course, from the user's point of view, he's not interested in which part of the network is congested. He is interested in performance end-to-end, from application to application. And of course, we will introduce some testing which will be done end-to-end rather than node-to-node, as it was done in this example. But in this our example, we could say that we know that the wireless link was the bottleneck of such a configuration, so maybe it was not such a big mistake as one can think, but of course end-to-end testing is also needed. And what we didn't do, and maybe we should, was interoperability between the devices. So we only used same devices on both sides of the wireless links and didn't try to interoperate between them. Maybe that is also an interesting topic for future work. Thank you. Questions?
Any questions?
Yes.
I was wondering, is there any other evidence that the encryption is really different than the fact that the only difference? Oh, okay. My question is, how did you come to the conclusion that the encryption is the difference between the two devices, other than that it's the only difference that you know of?
You made the point exactly. That's the only difference that we know of. So it is at this point of time our assumption. Maybe we should do some other testing, but at that point of time we just didn't come up with a way how to check it.
Okay.
Yes. Okay. No, we tested only UDP performance. Because traffic generators, this software traffic generators, very simple tool, only provide you with UDP testing. Of course, TCP testing is one that should be written here also. Yes. Yes.
How about cross traffic? Was this done during normal operational hours, where there was other traffic there as well, or?
Even though I said the traffic, the network was operational, at the time of the testing there was no users on any of the location. So no other users, exclusively our traffic.
Any further questions? One at the back.
In view of the known vulnerabilities of web, have you considered the option of simply not using it?
Yes, but as I said, we only took the network that was already implemented, and someone else designed it, and someone else predicted that it will be. It is an obligation to use encryption. So I think that security is always an issue of balancing things. You want to keep simple and useful, or you want to keep things secure. In my opinion, yes, it could be done. We could turn off the encryption and maybe achieve better results. But that was a political question, not a technical, at that moment.
Okay, if there are no more questions then, I'd like to thank Igor again. And that also concludes this afternoon's session on network management. Thanks once again to all three speakers, and coffee awaits.